Video is about a fun little theorem called the squeeze theorem. There are two conditions, hypotheses, to the squeeze theorem. First, if we have three functions, if f of x is greater than or equal to g of x and less than or equal to h of x, in other words, f of x is between g and h, in the neighborhood of C, which means for some open interval around the x value C, we know the f of x has to be between g and h. And we also know, switch colors because there's a second condition here, and we know that the limit of g of x as x approaches C and the limit of h of x as x approaches C are equal to each other. That means that the limit of f of x as x approaches C must equal that same limit. Actually, what I'll do is I'll say that the limit of g of x as x approaches C equals the limit of h of x as x approaches C, and we'll just give that limit some name. So the limit of f of x as x approaches C also equals that same thing. It's sort of a silly rule. What the rule says, I'll just kind of draw a little diagram for it, is if you have three functions, g of x, h of x, and f of x is always in between the two, and then at some point C, label C here on the x-axis, at some point C, you can see that the green function and the blue function, they both have the same limit here. So that's our L, that y value where the green function and the blue function are coming together there. That means that the red function, which has to be between blue and green, is literally squeezed into that spot also. They must all have the same limit there. That's the squeeze theorem. First, I'll show you an example, and then I'll show you why we actually use it today. We'll just look at this top one here. The limit of x squared times the sine of 1 over x. So, as x approaches 0. So, what we're going to do is take the sine of any number. So we know that the sine of whatever number, the sine of anything is between -1 and 1. So we'll write that to start with. -1 is less than or equal to the sine of 1 over x, which is less than or equal to 1. We know that because sine is always between -1 and 1, which means if we were to take that inequality and multiply all three sections of that inequality by x squared, which is always a positive number. So when we multiply both sides, or in this case all three sections, by x squared, we don't have to change the inequality symbol. But what that would leave us with is that -x squared is less than or equal to x squared times the sine of 1 over x, which is less than or equal to x squared. So the function that we care about, x squared times the sine of 1 over x, is always between -x squared and x squared. And we also know that, so by the way, that's the first condition of the squeeze theorem, that the function we care about is in between two other functions. And we can say that the limit of -x squared as x approaches 0 and the limit of +x squared as x approaches 0 are both equal to 0. So if x squared times the sine of 1 over x has to be in between or equal to -x squared and x squared, and when x is approaching 0, negative x squared and x squared are approaching the same thing. That must mean, therefore, these three dots is a symbol you might have seen before for therefore, the limit of x squared times the sine of 1 over x as x approaches 0 must also equal to 0. And that's just the squeeze theorem in action. Since we have negative x squared and positive x squared, and some other function that is always in between the two, sine of 1 over x is always in between, sorry, x squared times the sine of 1 over x is always in between the two. Well, since they all come, since the two that we know about come to the same point here, that means the red one in the middle is squeezed into that model. So that's an example from a recent AP exam that uses the squeeze theorem. To be honest, that's not why we care about it today, though. The reason why we care about it today is because of a very specific few functions. And they are all related to this little diagram here. So I'm going to do this quickly. This is a unit circle, which means the radius is 1, which means this radius is also 1, and this radius is also 1. And I'm just realizing now that this is the wrong spot. That's better. Okay, so if we use some basic trig using this right triangle out here, we can say that the opposite leg of that triangle over the adjacent leg is the tangent of x. And since the adjacent leg is 1, that means this opposite leg is the tangent of x, which means the area of this big triangle would be 1/2 base times height, or 1/2 tangent of x times 1. So I'm going to put that here. Tangent, 1/2 tangent of x. A slightly smaller shape is this circle sector in here, which you can see is smaller than the triangle I just drew, but bigger than that innermost triangle. So smaller than tangent of x over 2 would be this circle sector. And you might not remember this, but we'll come back to it later in the year. The formula for the area of a circle sector, let's write the formula over here, is 1/2 r squared times theta, where theta is the measure of that central angle. So in this case, that central angle is x, and the radius is still 1. So 1/2 r squared theta is 1/2 times 1 squared times x. So that was a shape that was a little bit smaller than the triangle whose area was tangent of x over 2. So tangent of x over 2 must be bigger than theta over 2. Sorry, not theta, x over 2. Remember that x over 2 is 1/2 times 1 squared times x, because x is the central angle. Okay, and then there's one more shape in here to look at. It's this innermost triangle in here. And to find the area of that innermost triangle there, we would need to draw the height of that triangle. And now the height here, since this triangle has a hypotenuse of 1, and this height is the opposite leg in a right triangle, this height here would be the sine of x, because the sine of this angle would be the opposite over 1. And so the area of that triangle would be 1/2 base times height. 1/2, the base is 1, times the height of sine, 1/2 sine of x, or just sine of x over 2. And that triangle is smaller than the circle sector I drew before. So tangent of x over 2 is bigger than x over 2, which is bigger than the sine of x over 2. I'm going to play with these for a minute. First thing I'm going to do is drop the 2's. There's no reason for them. The tangent of x is greater than x, which is greater than sine of x. And to be honest, in theory, x could be 0 degrees, if that was all the way down there, in which case all of these would be 0. So let me just put an or equal to there. So we'll keep using or equal to. Okay, I'm going to do a little bit more here. I'm going to divide all three parts of that inequality by the sine of x. The reason I can do that is I'm talking about a triangle here, so the sine of x is going to be the sine of an acute angle, so it's positive, so we can do that without ruining anything. Dividing everything by the sine of x, so that becomes x over the sine of x in the middle. Sine of x over the sine of x is, of course, 1. And the tangent of x divided by the sine of x is just 1 over the cosine of x. If you're not sure how, take a second to work it out and figure out why. Okay, keeping on going with this for a second, though. The next thing I'm going to do is invert, or take the reciprocal, I should say, of all three pieces of this compound inequality. You can do that, right? You know that if, let's say, x equals 3, then the reciprocal of x would equal the reciprocal of 3. That's just a basic property of equality that you know. The only catch is when you're dealing with inequalities, you've got to be careful. You've got to flip that inequality around. Because if x is something less than 3, then the reciprocal of x is actually going to be bigger than the reciprocal of 3. Think about an example there. You know that 2 is less than 3, but 1/2 is bigger than 1/3. So if I take the reciprocal of all of these, the cosine of x, sine of x over x, and the reciprocal of 1 is still 1, I'm now flipping around my inequality symbols. Cosine of x is less than or equal to sine of x over x, which is less than or equal to 1. Now, at the same time, I'm also going to point out that when the, actually I'll just use this as my graph. If I look at those three functions, cosine of x, let's just look at cosine of x and 1. Cosine of x, we know, looks like this. Y equals 1, of course, just looks like this. And notice how when x is approaching 0, they're approaching the same thing. The limit of the cosine of x as x approaches 0 is the same thing as the limit of 1 as x approaches 0, and both of those are just equal to 1. Well, since the sine of x over x is in between the cosine of x and 1, somewhere in here, well, because of the squeeze theorem, it is literally squeezed into this spot right here, and so that means that the limit, that color's terrible, the limit of sine of x over x as x approaches 0 is also equal to 1 because of the squeeze theorem. We've got the two conditions. Sine of x over x is in between two functions, cosine of x and 1, within the neighborhood of 0. And those two functions, cosine of x and 1, both have a limit as x approaches 0 of 1, which means that the sine of x over x must also have a limit as x approaches 0 of 1.